The CapSat-1 CubeSat mission proposal was a continuation of what this program accomplished, the Weiss CubeSat Development Team, or WCDT. This program originated in fall of 2015, and its goal was to build, test, and fly a CubeSat in the span of 3 to 4 years. A CubeSat is a small nanosatellite with a standard dimension of 10 by 10 by 10 centimeters, and it is commonly used by universities and small companies in hopes of executing scientific technical payload missions in the space environment. The Weiss CubeSat development team submitted a CubeSat proposal to NASA's CubeSat Launch Initiative Program, or CSLI, in 2016, known as the WISeSat-1, named after the school that it originated with, the Weiss School, located in Palm Beach Gardens, Florida. The mission was eventually selected by NASA CSLI in 2017, and the WCDT developed the WISeSat-1 CubeSat itself until its eventual launch in December of 2018. Alongside this, the WCDT also developed an aerospace public policy team to work in cohorts with the WISeSat-1's development in hopes of advocating and communicating the significance of CubeSats and the CubeSat Launch Initiative program in schools on the state and national level. While we were developing the WISeSat-1 mission, we were also able to submit 5 CubeSat proposals to NASA CSLI in the fall of 2018. I had the opportunity of leading one of these proposals, the CapSat-1 proposal, and it was eventually selected by the CSLI in their 10th annual round of missions in March of 2019. At the time of the mission proposal submission, I was in 7th grade, and the mission is to validate a novel capacitor-based electrical power system in a 1U CubeSat. To ensure that the CubeSat itself will be ready upon its launch, we developed many reviews for it, including the Preliminary Design Review, or the PDR, the Mission Definition Review, or MDR, and the Critical Design Review, or CDR, of the mission, which all work in compliance with NASA's Systems Engineering Handbook, as you can see in this image. And that engineering handbook provides many pieces of information in developing a scheduled mission lifetime plan for a CubeSat before it is launched. The primary mission statement for the CapSat-1 mission, along with all the other proposals that we submitted to the CSLI in 2018, all tie back to education, providing opportunities for middle school students to engage in hands-on experiential learning and to develop their skill sets in the aerospace and engineering workforces of the future. Since the WCDT program traces back to a K-8 public or private school program, education is of the main priority of the CapSat-1, and it'll provide educational opportunities for young middle school students and younger to eventually apply that knowledge to the STEM workforce of future generations. The secondary mission of the CubeSat, namesakingly, is the demonstration of a novel capacitor-based electrical power system in a 1U CubeSat, and it is a technological demonstration category. A capacitor is a type of battery much smaller in form than what is used in the status quo of the electrical power system, or EPS, component of the CubeSat, known as the lithium-ion polymer battery. The LiPo battery is mainly used in CubeSats because it has a very high energy density, meaning it has the ability to store charge for a very long period of time. Though it does have that ability, it's also very dangerous to the internal components of a CubeSat because that stored charge can result in the battery short-circuiting and damaging its surrounding components. And it has also been proven on Earth that capacitors are much more durable to different temperature extremes than lithium-ion polymer batteries, which is definitely applicable to the space environment. The WISeSat-1 mission relied on a company known as Near Space Launch Inc. to provide many important structural components to the CubeSat. And as the CapSat-1 is also a 1U along with the WISeSat-1 mission, we will be utilizing Near Space Launch Inc. as well. The payload of the mission, though, will be gathered from a company known as Maxwell Technologies with their 2.5 farad capacitor variant. And there will be 2 sets of 10 of these capacitors, overall alluding to 20 capacitors in total, and 2 sets will each be in series inside of the 1U CubeSat. Those will be powering the internal components of the CubeSat, since the payload will also be integrated with the CubeSat's electrical power system. This EPS will be provided by Near Space Launch, along with their I-3 omnidirectional patch antenna for communications. And the EPS component will also work in combination with the NSL standard fast bus solar panels, which will provide power to the rest of the CubeSat. The methods and procedures of the CapSat-1 will be applied from the success of the WISeSat-1 in hopes of getting that same success with the mission. Since the CubeSat will not be necessarily relying on lithium-ion polymer batteries, but capacitors, and because capacitors do not have a very high energy density, the CubeSat itself won't be charged when it is deployed, but it'll only be charged after its deployment when it's in orbit, opposed to regular CubeSats that have the lithium-ion polymer battery fully charged before they're deployed. So upon the CapSat-1's deployment from the International Space Station, it'll receive telemetry data when the capacitors are fully powered up using the mission's solar panels over time. And this cycle, this repetition cycle, will take place over a time period of around 6 months to a year. And in the event that one of those two sets of capacitors fail, they'll be able to directly rely on the other set and giving power to the rest of the CubeSat. There were two primary pieces of theory and calculation that the CapSat-1 relies on with its mission, and those trace back to the energy density formula of a standard battery and the standard charge and discharge curve cycle of a regular capacitor. And as I stated before, capacitors have a very low energy density, meaning that their charge and discharge cycles are much less sinuous like a lithium-ion polymer battery and are very quick in interval spurts over time. As you can see in the image shown, a discharge curve of a capacitor is very exponentially decreasing with a very low time period for each capacitor. So the CubeSat that will be testing the CapSat-1 will be testing the effectiveness of a capacitor charging and discharging in radiation conditions of space over time. The longer it takes for this capacitor to charge, we know that it is more efficient because it can store that charge for a longer period of time. And being able to measure that time interval in the conditions of space will be beneficial in proving that capacitors can be beneficial to CubeSats. And the second equation shown in this image here is of energy density. And as I stated before, lithium-ion polymer batteries have a much higher energy density than capacitors because of their chemical composition. But being able to measure the standard effective energy density of a capacitor in the space environment will prove that it's effective compared to lithium-ion polymer batteries per their unit volume in space. The equation shown here, U, the effective energy density, is equal to 1/2 of the battery's permeability in free space, or its magnetic field strength, multiplied by its electric field strength squared, divided by 2. And as a middle school student developing the CapSat-1 mission, I was able to develop a science fair project, hopefully validating the mission statement of the CapSat-1 in my 8th grade year. The mission, or the project, was testing the effectiveness of two different types of capacitors, one of 1.5 farad capacitance and one of 2.5 farad capacitance, in a simulated space environment in the confines of a thermal incubator compared to the control of a lithium-ion polymer battery. We actually found from this experiment that the 2.5 farad capacitor, as you can see by its discharge curve here, was actually more efficient per unit volume than a lithium-ion polymer battery. And we took that into account by dividing the total amount of time it took for the capacitor to discharge divided by its unit volume, and we did the same for the discharge time of the lithium-ion polymer battery per its unit volume. And though those were the preliminary results of the CapSat-1 through a science fair project, we expect that the CapSat-1 mission will elevate beyond that, and that we will get very important data from the mission's capacitors for the future of the EPS component in CubeSats. The mission, as stated before, will probably span within around 6 months to a year, and we hope to get repetitive cycled information in the form of telemetry packets on the mission's current, voltage, discharge time, and mean energy density over a period of time in orbit. And to conclude, the goals of the CapSat-1 mission are threefold: to technologically validate a novel capacitor-based electrical power systems technology that we could potentially use to grow the demand for CubeSats being launched, again in its secondary mission statement, to revitalize the CubeSat market industrially in hopes of providing new evolution in how the EPS component is viewed in a one-new CubeSat, and in the primary statement, to provide young students the opportunity to develop CubeSat through hands-on experiential learning in hopes of giving them the applicable knowledge of future STEM workforces. I would like to thank Near Space Launch Inc. for providing the materials and components for the CapSat-1 mission before its eventual launch in around late 2021 to early 2022, the NASA CubeSat Launch Initiative Program for funding for the integration and launch of the CapSat-1, NanoRacks LLC for providing information for the integration of the CapSat, and the Aerospace Public Policy Institute for giving me the opportunity to advocate on the importance of the CapSat-1's mission both statewide and nationally, and for the Blue Cube Aerospace Incorporated company for sponsoring the CapSat-1 mission.